In today's video, we're going to be deriving a rule for counting the number of factors that a number has. In the first part of the video, we're going to use a simple example to understand how and why our rule works. But by the end of the video, we're going to apply our new rule to a much larger number and solve quite a tricky problem. Let's get started. The first step then in our factor counting experiment is to have a look at a number we already know a lot about, and that's 24. So to start off with, we're going to list the factors of 24. 24 has got factors of 1 and 24, 2 and 12, 3 and 8, and 4 and 6. We're not really worried about what the factors are, we care about how many there are. And in this case, there are 8 factors. So I'm also going to write that down. There are 8 of them. Well, now we need to think about, this is nice, but can we come up with some sort of rule to help us predict the number of factors that a number has? And to do that, we need the number's prime factorization first. So for 24, we can break it down like so. Could go into 6 and 4. 6 can break down into 3 and 2, and 4 can break down into 2 and 2. I'm going to circle all of the prime factors. And what this gives us at the end is that 24 can be written as 2 to the power of 3, because there's 1, 2, 3 powers of 2, multiplied by 3 to the power of 1. Okay, so far we haven't really done anything groundbreaking. This is the part where we think about a new insight, though, that gets us to our factor counting rule. And what we need to do is link our powers of our prime factors, which are 3 and 1. We want to link those to our 8 factors that we know we've got. It's not immediately obvious what to do, but here's how the factor counting rule works. You add 1 to each power. So we've got 3 add 1 and then 1 add 1. If we added 1 to each power, then we would have 4 and 2. Now it should be more obvious where this 8 is coming from. We multiply those two numbers together to get our number of factors. For the second part of this video, we're going to think about why this counting factors rule works. And again, we're going to look at 24 for our example, just because it's a nice size to work with. So starting off then, we're thinking about the prime factorization, and we'd like to think about how we actually get factors from this. So let's have a look. For any factor of 24, it's allowed to contain up to 3 lots of 2, isn't it? 3 powers of 2. So let's think of some options that we could have. We could have 2 to the power of 1 contained within our fraction. We could have 2 to the power of 2, or we could have 2 to the power of 3. They're all options to be within our factor of 24. And we also can't forget that 2 to the power of 0 is a valid option. 1 is definitely a factor of 24. And I'm going to write these as a set, so with some nice curly brackets. We can do the same thing then with our 3 to the power of 1. because any factor of 24 1 is definitely a factor of 24, and so is 3. So any factor of 24 is allowed to contain up to 1 power of 3. Well, now maybe it's getting a bit more clear where the 8 comes from, because this set has size 2 and this set has size 4. What we're interested in is choosing factor pairs which come out of these two. So an option for us, if we consider, for example, 3 and 8, well, we chose our 3 to the power of 1 from here, so the other number has to be 2 to the power of 3. If we think about a different pair, like 12 and 2, well, we took a 3 to the power of 1 and a 2 to the power of 2, so the other number had to be 2 to the power of 1. The second number is always dependent on the first. So what we're really asking is how many different combinations of number can we choose from a group of 2 and a group of 4 together. And at that point, we know there's this rule of counting, you just multiply the size of the two sets together. That's where our rule comes from then. And I think it's worth at this point writing it down maybe a bit more formally. So for any number, for some number n, if it's got a prime factorization that goes like this, could have p1 to the power of n1, so that's a prime number to the power of a number. p2, n2, we've got another prime factor to the power of some number. So if it was 24, it would be 2 to the power of 3, 3 to the power of 1. Well, let's keep going in ours because we want to make this a bit more general. Up to p to some k, it's got k prime factors, and we can say this is to the power of n k. Yeah, this is the prime factorization of a general number. Well, we can say the number of factors total number of factors altogether can be written as n1 plus 1 multiplied by n2 plus 1. So these are the powers plus 1 each time. Dot, dot, dot. Multiplied by nk plus 1. That is our rule for counting factors, written out a little bit more formally. We add 1 to each power in the prime factorization, multiply them all together, that gives our number of factors. In this part of the video, we're going to apply our new factor counting rule to a number, 360. And I've chosen 360 because it's got lots of factors, so it'd be too annoying to try and list them all out normally. Well, let's have a go then. So first of all, we want to do a prime factorization for 360. So I'm going to choose to break it up into, it could be 90 times 4, so you can do whatever you like for this bit. 4 would go into 2 and 2, 90 could go to 9 times 10, so 3, 3, 5 and 2. So writing out our prime factorization then, this is the really helpful bit. We've got 2 times 2 times 2, so that's 2 to the power of 3. We've got 2 3's, so we've got 3 to the power of 2. And we've also got 1 power of 5, which is a little bit messy. So times 5 to the power of 1. So now's the part where we have to remember our rule for counting factors. And what we have to do, so I'm going to write underneath, for the factors, we have to add 1 to each power. So we're going to take 3 and add 1. And then 2 was the other power, we need to add 1. And then 1 was the third power, so we need to add another 1 to that. And we need to times these numbers together. So we're going to get 4, 3, and 2. And we need to times 4 by 3 to get 12, times by 2 again to get 24. So our idea with our new rule is that we think 360 has got 24 factors. If you like, you could go through and list them all, but I'm happy to just believe the rule at this point. In this final part of the video then, we're going to leverage our new rule to find the number of factors that 86,400 has got. First of all then, we need to think about the significance of this number. Like we got told, it's the number of seconds in one day. So first of all, breaking it down into some more manageable chunks, the number of seconds in one day, well, there's 60 seconds in 1 minute, there's 60 minutes in an hour, and there's 24 hours in a day. So we can straight away write our number as that. The reason for doing this is because a prime factor tree for a number that large is just annoying, but you could do it if you want to. Our second step then should be writing these as index powers of their prime factors. So thinking about 60 first of all, 60 can be written as 2 to the power of 2 multiplied by 3 to the power of 1 multiplied by 5 to the power of 1. You can check me if you like. We have another 60 there, so we can write it the same way. 2 to the power of 2 multiplied by 3 to the power of 1 multiplied by 5 to the power of 1. And 24, like we saw earlier, can be written as 2 to the power of 3 multiplied by 3 to the power of 1. Well, now what we need to do is put all of these together into one massive index power. So we're going to have some powers of 2. We can write this up here. We've got some powers of 2, we've got some powers of 3, and we've got some powers of 5. Thinking about our index laws, well, if we multiply numbers together, we need to add their powers. So my powers of 2, I've got 2, add 3 to get 5, add another 2 to get 7. My powers of 3, I've got 1, 1 and 1 to get 3 in total. And my powers of 5, I've just got 1 and 1 to get 2. So at this point we've obtained the prime factorization of 86,400. 2 to the power of 7 times 3 to the power of 3 times 5 to the power of 2. Well, now we think about our counting factors rule. And the first part was writing out these 3 powers, or however many powers we would have. We've got 7, 3, and 2. Step 2 is to add 1 to each of these numbers. So we've got 7 plus 1, 3 plus 1, and 2 plus 1. And now we need to multiply these together. So we're going to have 8 multiplied by 4 multiplied by 3. 8 times 4 is 32, times by 3 is 96. So our answer here is 96. And what that means for us, if I can hold on to my chalk, is that 86,400 has got 96 factors. I hope you would agree if we didn't have our factor counting rule, this would be pretty much impossible. or at least take a very long time.